Hello. Purpose of today's video is to do sort of a brief or hopefully brief summary of the concept of finding areas using integrals. So using integration to find areas of irregular or awkward looking shapes. So in the first case, I'm going to find the area between the curves, and both of those curves are parabolas. I found this graph using technology. I also found their intersections using technology. And when I wrote all this stuff on paper, as it were, I made sure to label all the important pieces, like what is the upper curve, what is the lower curve, and what are the intersection points. Also, it's worthwhile to prove that you can use algebra to find those intersection points if the algebra skills are available to you. So in this case, I just have one quadratic equals another, and when I collect like terms, I end up with this expression, which is factorable. It gives me x equals 0 or x equals 2, which is when x is 0, when x is 2. Those are the two intersection points. So to find the area between the two curves, I simply have to integrate from 0 to 2 the y upper minus y lower with respect to x. Here's the y upper, here's the y lower with respect to x. So there I'm going to distribute. Don't forget to put parentheses in here, and that way you'll remember to distribute the negative, hopefully. So you'll end up with 4, and this was a typo, this should be 4x minus 2x squared dx, which, taking the antiderivatives, and gets us 2 2/3. Now, first of all, I went through that really quickly. If you want to make sure that you understand all the work that I did up here, pause the video, take a moment to study the screen and make sure that you agree with what was said. But I wanted to talk to you about the thinking part. You see what I did right here is I drew a rectangle over my graph, and the dimensions of the rectangle are just a little bit bigger than 2 by 1. So this is just about taller than 2, and this is 1 wide, and so the area of this rectangle is near 2. Imagine, if you will, taking this rectangle and tilting it so that it covers most of the space you see here in this irregular shape. I'm using the rectangle to make sure that the 2 2/3 is reasonable and that I didn't make some silly mistakes with negatives. If, for example, I got 12 2/3, or if I got anything that's in the teens, and then I look at my rectangle and I'm like, wait a second, something's not working right. So think about what answer you should get before you actually start doing the work, or even after, just think. Alright, the second exercise is really a technology-based kind of thing. So I went to the calculator and I graphed the first curve and the second curve. Important thing to notice in this case, though, is that I'm going to write this down first. And then alright. The thing that we need to notice is the only part of the function I'm interested in, or functions, is x is between 2 and 7. So I dotted the parts of the graph that don't matter, and then I made solid graphs from 2 to 7, because this is the part that actually matters. There's intersections over here, but we're not going to worry about those. It does say, though, they intersect at points A and B, find the coordinates, the x-coordinates of A and B, and that's what I did right here. I'll show you how I did that using technology as a quick refresher. You can see I entered y1, I entered y2, so we have the two curves. I'm going to get a nice looking graph here. Actually, hold on. Never mind. Oh, there we go. I'm going to go to calculate. So you hit second, trace, and then choose option 5 for intersect. I'm going to have to wait for the graph to draw anyway. I might as well do two things at once. So we wait for the graph to draw. And then the calculator is going to prompt me what is the first curve you want to see an intersection for, what is the second curve you want to see an intersection for, and so on. Important thing to recognize is when it asks me about first curve and second curve, here is where the cursor is. The computer will give me the closest intersection to that cursor. So if the cursor is right here, the computer is going to give me that intersection. So when I hit enter, that says the first curve is the blue one. Second curve is the red one. Yes, I agree, so I hit enter, and then I hit enter again after I guess 2.8717. That's exactly what I was going to guess too. So I quick jot that down into the margins, and because I'm going to need this for the problem, I quick write that down, and then I'm going to do second trace again to find the other intersection. But before I do hit enter, I have to Nintendo over. So I basically want to make sure that this cursor is closer to that intersection. I pushed down first so I could pop onto the red curve because it's a shorter distance. It's going to take me less time to get there. Now we can see the cursor right here is closer to the intersection that I want, so I will hit enter here 3 times, and it gives me the value of x for the second. So that's where I got these two numbers. These are the boundaries then of the curve, the area between the two curves. So that's what we have to find next. Find the area enclosed by the two graphs where x is between 2 and 7, and particularly we're finding the area between the two graphs of the intersections. So essentially I'm looking for this area right there, just the shaded portion. Just as before, the area is the integral from one boundary to the other. The upper curve subtract the lower curve. So the green is the lower, the purple is the upper. Now this is again, if you ever see that you're asked to integrate a product of two unique functions, like an exponential function and a squared function, if you ever have to do that, realize that in this course we do not have the skill set to do that, and we must use technology. So it's the product of two unique functions that'll be sort of a clue that this is going to be a calculator-based kind of question. So I do go to the calculator, and it produced area equals about 6.76. Show you how to do that real briefly. We have the two functions written in here, but what I'm going to do is I'm going to unhighlight them because I don't want to see their graph anymore. I want to see what happens when we take the upper curve, this is the upper curve, minus the lower curve, which is y1 minus y2. So I'm going to go alpha trace, and that pulls up my y1s and so forth. So we're going to go y1, so I hit enter, and then I'm going to hit minus, and I'm going to go alpha trace again, and I'm going to choose option 2 for y2. So this is a graph of y1 minus y2. So we are going to go to calculate, and option number 7 for integral of f of x. So here's what the graph of the difference of those two functions looks like. Just going to wait a little while here. And then I'm going to integrate from the boundaries. So it says the lower limit, it's asking me for the lower limit, and recall that that was 2.87. Oh, sorry, I just made a mistake here, hold on. Oh no. Okay, bear with me. 2.87, so we're going to go 2.87. Enter, and then the other limit was 6.78. 6.78. Enter. It's going to cruise across here, and it's going to give me the answer to my question. The area between the two curves is, and it says about 6.7589 or so. So, returning to my writing project. Alright. Sorry, this is taking me a second here. We needed to find the shaded area right there, and I wrote out the integral, and then I went to a computer and I found 6.76. So I showed you how to do that with the calculator. Let's see if we can fly through the rest of this stuff a little quickly. Again, if you need to think a little more, then you can pause and reflect, but I'm just going to tell you the facts and you absorb them the way you know how. So the first case, we have a square root function and a linear function. The graph's going to look like this. We're looking for the area bounded between the curves and the y-axis. So essentially, when you look at the description, it's this little triangular-ish kind of shape that I'm looking at. So all I have to do here is show the difference upper minus lower. So the red is the upper, the blue is the lower, and find the antiderivative of each and evaluate from 0 to 4. I know 0 to 4 because that's the point of intersection right here. You can find that algebraically if you need to, but in this case, you know, just common sense and looking at the graph, that's how I got that. So, anyway, it turns out that the area is 10 2/3. Again, pause the video to make sure that you understand where each of these numbers came from and why 10 2/3 is valid. Also, if this is a test, you should probably go to the calculator and make sure that 10.6667 is the value of the area when you subtract the two curves. Now the second problem is interesting because it's the same two functions, but this time it's describing the area bounded by the x-axis in the two curves. So we're talking about this stuff down here. Now most of the time when I ask students this question, they'll probably find a couple of integrals and do a bunch of fancy pants math, but the fact is we can use a little bit of common sense in geometry. You see this red triangle, if I outline that red triangle, it's a 6 by 6 right triangle where this is the base of the triangle and this is the height of the triangle. So the area of that triangle is 18 units. Now the area of the shaded portion in the previous exercise was 10 2/3. So to find the area shown in this picture, all I have to do is take the whole triangle 18, subtract the 10 2/3, and I get 7 1/3. Now if you're going to work harder, not smarter, then you would use integrals. Notice how I set up my integrals. Right here I went from 0 to 4 of the square root of x. So I just integrate the square root of x from 0 to 4. That's going to give me the left half, or the left portion of the shaded area. And then to get the right portion of the shaded area, I just need to go from 4 to 6 underneath the red line. So I integrate the red line from 4 to 6 to give me this little triangle wedgie, and I integrate the blue curve from 0 to 4 to get the other portion of the shaded area. And when I do so, take the antiderivatives, evaluate at each of the endpoints. No surprise, it turns out to be 7 1/3. So you can do this the easy way or the hard way, depending on how aware you are of what the question is asking and what information you already know. Last but certainly not least, we've got here this another technology problem. I know it's a technology problem because e to the x and the sine of 2x are being multiplied together. When two unique functions are multiplied, that's not something that I can use my limited integration skills to evaluate. So I'm going to go to the computer on this one. The first question is asking me there's an x-intercept at the point A. Write down the coordinate of A. I use my calculator and I find the x-intercept is 2.307. It also says find the x-coordinates of P and Q, the maximum and minimum respectively, and I found P and Q to be 1.017 and 2.588. And then, and I'll show you how to do this in just a moment. The last question was find the integral from P to Q of f of x dx using technology. So what they're asking us for, since P is 1.017 and Q is 2.588, and f of x is all this smudge right here, then all we have to do is put that into the calculator, and I got 9.96. The last portion said explain why this is not the area of the shaded region. Recall that the shaded region is from here all the way to here, from M to N, and there's a portion underneath and there's a portion above. This integral, the integral that we saw on the previous slide, is going to give me a negative number for this chunk and a positive number for that chunk. So it's not going to represent the total area, rather it's going to represent, excuse me, the net area. So my write-up said this is the net area, not the total area. The part of the graph below the x-axis gives the negative area, which is subtracted from the area above the x-axis. So just giving you some indication that you understand that this is not the total area in the picture because of the negativity. And we would actually, a better improvement on this answer is if you want the total area, take the absolute value of the function and integrate from P to Q. So quickly now, I'm pretty much done. If you want to make sure you know how to use the calculator to answer the questions from the last problem, I'll walk through that really quickly. So I've got the, as quickly as I can anyway, I've got the function here as y4, so I'm going to clear the rest of these. Don't need them anymore. Done. And I'm going to highlight that. And then luckily the graph had a viewing window all set for me, so the x's went from up to 4, so I'm going to go up to 5, give myself a little breathing room. The y's went from -5 all the way up to 15 and counted by 5, so I should get a graph that looks like the one on the page. And there it is. So the first thing I had to find was the x-intercept. So to do that, I'm going to go to calculate. 0. 0 is the mathy word for x-intercept. So it said right bound. You need to be to the right-hand side. First of all, it said left bound. I hit enter already. You need to be the left-hand side of the intersection, or the 0. And then you need to move over to the right-hand side of the x-axis, or x-intercept, and hit enter. And then you ask the calculator to do the work for you, and it comes back with 2.307, which is what I had for the x value, or x coordinate. Next, also asked me to find the maximum and the minimum. You go to calculate. For the maximum, you choose 4, and we just go from 0 to 2. You can kind of see that the maximum occurs between when x is 0 and 2, so I just let the calculator do the work, hit enter, and it says 1.017. You can do the same thing by pressing minimum to find that guy down here. And the last thing that we needed was to calculate the integral, and the lower limit was 1.017, and then the upper limit was 2.588, and it should come out as 9 something, and sure enough it says 9.9617 blah blah blah. So that's how you use the technology to answer all your questions. That should help you, I hope, with the review. All the basic topics that we need to be responsible for are covered in this here video. So please make sure that you not just view it, but you view it for understanding. Take your time. Thank you for watching and have a great day.